Okay, main event here is we want to figure out how to find the derivatives of the basic trig functions. So by lesson's end, we want to figure out things like this, right? How do you find the derivative of the sine function, or maybe even something like this? Right? When you differentiate the tangent, what do you get out of that? So to start things off, we talk about some basic limits that we haven't talked about previously, and they're pretty fundamental ones. So these you can find in any calculus book. So this is an example of a simple limit. The limit of the sine of x over x as x approaches 0 is equal to 1. And just like our earlier treatment of limits, the best way to do this perhaps is to look at a table, right? So you can look at x values very, very close to 0, right? And then you examine the sine of x over x. And you find all of these values are clustered really, really close to 1. So this is an important limit that is related to the derivative of the sine function. So another one here that's pretty common in this section, one that deals with the cosine function. So the limit as x approaches 0 of cosine of x minus 1 over x, that limit is equal to 0. So these two are pretty common in serving as the foundation for differentiation for the sine and cosine functions. So I want to go through just a basic example here. So I'll hold up this problem here. We're going to go through and see if we can calculate what is the limit as t approaches 0 of cosine of t minus 1 over the sine of t. So I'm going to reproduce that right here. Okay, so something you can notice right away here is that this has the same problem as the earlier ones that we've examined when we talked about limits. So if you try to insert t equals 0, you get a cosine of 0, so 1 minus 1, and then divided by 0. So you get that same form here that we encounter quite often. Right? You get that 0 over 0 form. So all we want to do here is to modify this problem in some way so that we can make use, right, of these special limits. So what we can do here is to introduce an extra t, right? We can divide the top and the bottom by t and see what that accomplishes. So we're going to take a look at this limit here. So this will be the limit as t goes to 0. And now the top will look like the cosine of t minus 1 divided by t, and then the bottom portion will be the sine of t over t. Okay? So without writing too much here, the point here is you take a function that where it might not be obvious how these apply, and as soon as you divide by t, as long as these limits exist, right, in terms of the quotient, then that means you can take the limit to the top and take the limit to the bottom. And so if you look at the top function, this limit is exactly this one here. So this top portion here, this is going to go right to 0, and the bottom one is another special limit, and this one here goes right to 1. So when you calculate this limit, you end up with 0 over 1, and that's perfectly defined in mathematics. Right? So that limit is 0. So coming back to this problem, right, this is a variation of these special limits here, but you can modify it and you can figure out its limit. Okay, so the main event here is to figure out what is the derivative of the sine function, or what is the derivative of the cosine function. So we're really going after something like this. So what is this equal to? And it turns out that to figure this out, you would have to go back and use the limit definition that we talked about a little while ago, right? So this is the underlying definition of how we calculate or evaluate f prime of x, right? We would have to use it on this function here. So what I'm going to do instead is just to give a pretty simple geometric argument of this. Okay, so we're going to try to answer this question here. What is the derivative of the sine, or what would a graph look like that calculates the slope of the tangent line? So I'm going to sketch the sine wave here, perhaps just one period of the sine wave. So something like that. So this is just from 0 to 2 pi, right? Approximately what the sine wave looks like. And to answer this question, what you want to do is to look at the steepness of the tangent line to the sine graph at different points, and then you can mentally piece together, right, the graph of the derivative function. So there's a couple of places where if you look on this graph, it's pretty easy to determine the slope, and one of them would be at this high point right here. Right, you can see the slope there is 0, it's nice and horizontal, and the exact same thing happens here. So if you think about graphing the slope of the tangent line, this means the slope here is 0, so literally the y value of the derivative is 0. So the graph of the derivative will be sitting directly on the x-axis, just like that. So other places where you can look, you could see that the tangent line is sort of steep at this point. And so if you calculate this for the sine graph, the slope here is equal to 1, and it looks pretty reasonable on the graph. So when x is 0, we start up here, right? The slope is 1. And the exact same thing happens over here, right? So if you look at the slope at the edge, you can see that these look parallel. So the y value, right, of the derivative, you actually get 1 there. And finally, another location where it's negative is right about here where it crosses through. So the steepness of this line is -1. So that means if you think again of the derivative as a function, right, its y value here will be -1. So you come down here and you graph that. So what's interesting here, what you might notice, is that there are 5 green dots, right, that show up here. And what we're attempting to do is to graph the derivative of this function. And if you look carefully, this almost looks like a wireframe or a rough graph of the cosine graph, right? So if you were to consider all of the points in between the tangent lines that we sketched, you'd have a nice smooth function, right? So your graph would look something like this. And you'll recognize that right away, right? That this graph is the cosine graph. So it comes as no surprise, even though this isn't a proof, that the derivative of the sine graph is in fact the cosine graph. Okay, so we write this in calculus: the derivative of the sine of x with respect to x is equal to a new function, and that new function is the cosine of x. Okay, so this is just the way that we express this, right, in textbooks and everywhere else. So the sine of x, when you transform it under differentiation, you get cosine. Okay, and you can make a similar geometric argument or use the limit definition, and you could say a very similar statement for cosine, right? So when you differentiate the cosine function, you get the sine function back. There is a variation there, right? So it's negative sine. Okay, so the purpose of deriving these two new ones is to talk about new functions, right? And so that way we can find the derivative of different types of trig functions. So I'm going to close things off by doing a couple of problems, and this will be the first one that we focus on. And so you can see the purpose here is this has the sine function involved, but it's a more complex type of function. And all we're trying to do here is just to find the derivative of k. So we're asking this question, right? What is k prime of x? So looking back at some of the older things that we talked about, there are two functions at play here. You have an x squared, and then also the sine function, which we just learned about. So the best rule to apply here would be the product rule. So x squared is the first function, sine is the second. So when you find the derivative here, we're going to write down the first and differentiate the second. So we just learned what that is, right? That's the cosine function. And then we're going to add to it the opposite. So we write down the second, which is the sine of x, and then differentiate the first. So this would be 2x to the first power. And that's pretty much all there is to it, right? So this is using the old product rule, but we just have these newer functions. If you want to factor out an x here, you can certainly do that. So you can remove an x and see what's left. And this will be x cosine of x. Okay, and then this one here will have a 2. Better to write it out in front. Right, so that is what the derivative looks like here, x times this entire quantity there. Okay, and so we'll try one more problem here. And this one here is going to show us that not only can you just do ordinary problems like x squared times the sine of x, but you can differentiate new functions altogether, right? Something like the tangent function. So a big thing to note here is to recall that the tangent is a blend of sine and cosine. So we have to recall the definition here. So the tangent function is sine and divided by the cosine. So the moment we see that, we might think there's division involved here. Well, let's try the division rule, or the quotient rule. So we're going to give that a try. So to find y prime here, remember this rule requires a lot of space, right? It's a pretty long one. Okay, so we're going to have the bottom function, top function there. So the quotient rule here, it's the bottom function, the cosine, and then we differentiate the top. And so we saw that earlier, it's cosine. And then we're going to take away the top function, and this is the sine of x, and now we differentiate the bottom. Right? So this one we haven't used yet. Right? So the derivative of cosine is opposite sine. Okay, and all of this is divided by the bottom function to the second power, right? The bottom squared. Okay, so this is the derivative of the tangent function in raw form, right? We haven't really done any simplification or anything like that. Okay, so something you'll notice is you have a couple of negatives here, so you can change these to positives. And if you look really carefully, you can see something that you might recognize. So here we have cosine squared. Okay, we're just looking at the top with care, and then we're adding to that the sine squared. Okay, so this is that fundamental identity in trigonometry, right, the unit circle identity. So cosine squared plus sine squared for any same x or same theta is always equal to 1. So this derivative is going to simplify nicely. The top looks bad, but it's just 1. And then this is cosine squared, and this is the standard way of expressing that. And so the reciprocal of the cosine function is the secant function. So we can write this answer this way, and this is typically how it is expressed in math books, right? So if you have this new function, y equals the tangent of x, the derivative, right, y prime, this is secant squared of x.